See, the attendance has gone way back down again. That's a little disappointing. And hopefully a lot of you are just late. It's really not acceptable. I asked for some change, but it has not been a lasting one. It seems like it's just been for your midterm. Not good. Not good. Anyway. Happy Friday. Thanks for showing up. We have some remnants from packet 6 to do. Some of them are like this. We've got one variance left to do for the 5 sort of known distributions, and we're going to do that first. Then there's a computing application that's at the end. It's about 6 slides long. Not all of that is writing, of course, but it's going to take a fair whack of time, and probably we're not going to have enough to do that today. So we'll probably dig into the next packet worth of stuff. Okay, so that's on concentration inequalities, tail inequalities, and come back to max 3 sat on Monday. Okay, so that's the plan today. And Monday, let's do Poisson. Okay, so Poisson distribution is that funny distribution where the probability density function it sort of resembles that of a Taylor series that's been weighted or normalized so that its probability all totals 1, so it's been normalized by e to the minus lambda. It is, it does have an infinite range. It's one of those weird ones that has an infinite range. Anyway, we're going to compute the variance. Just to remind you a couple things, the expected value was lambda. That took a little bit of sweat for us to do, and I'm glad it ended up being lambda. Hopefully you are too, because that's the way lambda was defined, right? It's the average number of balls per bin, so the average case load, average load, okay, just average load. And we'll see what it ends up being for the variance. And just to remind you, what we're doing for the variance is a nice, neat little shortcut, okay, is to take the expectation of the variable squared and subtract off the square of the mean, and we have this mean to pump in there. So whatever we get as the expectation of the square of the value, we're going to subtract off lambda squared at the end. Okay, let's do it. Expectation of r squared. Okay, so when we weight this distribution by r squared, okay, so the original one weighted it by r, so we're multiplying by x squared, I guess I squared, because we're using I in the summation. We'll just make that infinity a little bit bigger. Okay, so it's I squared, and then times the probability distribution function, e to the minus lambda, lambda to the I over I factorial. Okay, and when we did this thing last time, things ended up being nice and neat because we only had an I here. We canceled this I with this I factorial, and then we just sort of rejigged the sum so that it looked like another sum. We can certainly do that for any I that's bigger than 0, right? Remember, if I is equal to 0, then this thing just kind of multiplies to be 0. And if I is bigger than 0, then you can cancel this with the first term of this thing here. Okay, so let's do that step. And sum from I equals 1 to infinity of I, e to the minus lambda, lambda to the I over I minus 1 factorial. Now, it would be nice if this thing was I minus 1, right? Then we could do the same trick. There's no reason that it couldn't be I minus 1. We can just imagine it to be so, right? And then it would cancel, and then we can do the same sort of technique that we did before. Now, we can't just write down I minus 1 without there being some sort of cost involved, right? We can't subtract 1 unless we add 1 right back on. Okay, so I want you to imagine that this thing actually is an I minus 1, which would be helpful so that it will cancel with the denominator. Sorry, I minus 1 factorial. Okay, so putting a minus 1 in there is, makes this thing not equal unless we add 1 back on. So that would mean, and I'm just going to break up the sum so that it is easier for us to follow. Okay, so this is just going to be one of these, right? So e to the minus lambda, lambda to the I over I minus 1 factorial. I'll give you a moment to catch up. So let's work with this term over here. Okay, first thing to note is that if I is equal to 1, then this first thing is 0, and multiplying by 0 is my favorite thing ever. So really, it's like the first term isn't there. So really, this sum can start at 2 instead. And if it does start at 2, then this I minus 1 will cancel with this I minus 1 in the denominator. Okay, we'll leave the sum on the right alone for now. So sum from I equals 2 to infinity of e to the minus lambda, lambda to the I minus 2 factorial, plus this one over here. Yeah. For this one? Well, just think about what happens when you sub in I equals 1, right? So the first term of this thing is 0, because you have I minus 1 in there, you multiply by 0, and it disappears. So we can rewrite this as the equivalent sum and just say it starts at 2 instead. And that's handy because, if we're going to divide I minus 1 into this I minus 1 factorial, it actually doesn't divide. 0 doesn't divide into 0 factorial. 0 factorial is 1, so there's not a common factor there. You can't divide 0 by 0. Right? So that's why we do that. Okay, now let's look at each of these. Okay. So this actually looks like the Taylor series that we're very happy with, right? It almost looks like the Taylor series. This would be the Taylor series if only this power, this I, matched this factorial in the denominator. If this had been I, or vice versa, if this had been I minus 2 in the power. It's easy to make this thing I minus 2. It's not so easy to make this thing I factorial. And the way you make it I minus 2 is you just write minus 2 there. Of course, you can't do that, but you can if you, multiply by lambda squared. Okay, so we're sort of dividing by lambda squared by writing minus 2 there, and we can multiply by lambda squared up here. Same sort of idea happens over here, right? This would be perfect unless, except for the power doesn't match the factorial. So we can make it so by putting a minus 1 in there, that's dividing by lambda, and we can multiply by lambda to the 1 to fix that. Okay, and it's not worth writing a whole line for that. Okay, but if you look at what the sum looks like now, when I is equal to 2, this is lambda to the 0 over 0 factorial. And when I is equal to 1, it's lambda to the 1 over 1 factorial, lambda to the 2 over 2 factorial, over 3 factorial, and so on. It starts at 0 factorial. This also starts at 0 factorial over here. Okay, so the final step, just to make it nice and clean, okay, we will rewrite this sum starting at 0. Okay, so lambda to the I over I factorial. Same one over here. Okay, I equals 0 to infinity of e to the minus lambda, lambda to the I over I factorial. And of course, each of these is the same, and it's equal to 1, as it should be, right? That's the sum of the probability density function. Okay, so that should equal 1. So we end up getting lambda squared plus lambda. Good. Okay, so that's only part of it, right? We need to finish this thing off. The variance is actually this minus the square of the mean, so the variance is expectation of r squared minus expectation of r all squared, which is lambda squared plus lambda minus lambda squared. That's lambda. Which is cool. So the Poisson distribution is a distribution where its expectation and its variance are the same, and it's both this load number. Yeah, I can't really, because the standard deviation is sort of what I think of as the actual units, and you'd be taking the square root of the load factor. But the load factor is sort of tying, is tied to how wide this thing is. So it is kind of a skewed-ish bell curve that isn't too wide. Its width is roughly tied to its mean, so it doesn't get too far out of control. That's the only intuition I have anyway. Besides this being really cool math coming out. Okay, good. Yeah. All right. Okay, so we've done it. We've gone through all the variances for all the major distributions, and here's a summary. So we started off with Bernoulli's or indicators. The expected value was the probability that that thing occurs. The variance is the probability that it occurs times the probability it doesn't occur. Okay, so that's small number. Uniform distribution, rolling an n-sided die, or any collection of, or any set that you want, all the things are equally likely. The average, of course, is just a straight average. It's not weighted. I mean, it's equally weighted. Okay, so it's just a straight average. The variance is the sum of all the squares of the things minus the average squared. And as a side note, and this is not something that I proved, but you can come to this result fairly quickly if you do the math. I'm not going to do the math, but we did the six-sided case. Okay, if you have the numbers 1 through n, so I'm going to call this an n-sided die. You sort of take the average of the top and the bottom. That's going to be, the expectation here is going to be n plus 1 over 2. That's pretty intuitive, right? N-sided die, or six-sided die, that would be 7 halves, and that agrees with what we had earlier. The n-sided die version for variance is not quite intuitive, but we did most of it, right? When we did the six-sided die, we added up a whole bunch of squares from 1 through n, used that formula, and then subtracted off the square of the mean. Most of the polynomials cancel out, and you end up getting a very clean answer. It ends up being n squared minus 1 over 12. The 12 in the denominator kind of comes from the 6 in the denominator when you add up all the squares. Add up all the squares, you end up with something times something over 6. And then you subtract off the square of this, which is over 4. Take a common denominator, that's going to be 12. It's amazing that it comes out so clean. And in the six-sided die case, that's 36, minus 1 is 35 over 12, which is, if you look back there, you'll see it's 35 over 12. But it generalizes to any number of sides. Interesting that it's over 12. Okay, a couple more things, but it's going to lead in well to our discussions about concentration inequalities. And this is one last example to talk to you about volatility. Anyway, here's the example. Okay? So suppose you have a gambling problem. This is a good problem to have, by the way, in that each of these has a positive expectation, believe it or not. Okay? So this is a gambling game where you're the winner on average per bet. Okay? So you can either play game A, where you win with probability 2/3, or lose 1 with probability 1/3. Okay? So you win $2 2/3 of the time, and you lose $1 1/3 of the time. Okay? So that's game 1. Where game 2 is similar to game 1, but it's scaled up by $100. So it's $100 on the win side, or minus $200 on the lose side. Okay, which game is better? All right, so let's figure this out. Yeah? First, we're going to compute the expected value of each game. Okay, the expected value of A. Okay, if you take the weightings of plus 2, 2/3 of the time, or minus 1, 1/3 of the time, you end up getting 4/3 plus minus 1/3, and that will give you 3/3, which is $1. Okay, so if you make this bet, you expect to win $1 on average. That's pretty good. The expected value of B is pretty much the same computation, except I've added $100 here and scaled it by 2/3, and I subtracted 200 here and scaled it by 1/3. Okay. And 2/3 of, that's in a ratio of 2 to 1 on, these things which are in a ratio of 1 to 2. So they're going to cancel each other out. If you don't believe me, you can do the math. 2 times 102 is 204. 1 times 201 is minus 201. And so we end up with plus 3 again. 3/3 is $1. Okay, so it seems like the games are the same, but the variances are different. And if you do this computation using the shortcut method, which I always recommend, 2 squared times 2/3 plus minus 1 squared times 1/3. Okay, so that's the expectation of R squared, and then you subtract off the expectation squared. Okay. Anyway, we have 4 square dollars, I guess, multiplied by 2/3, that's 8/3. Over here we have another third, so that'll be 9/3. That's 3 minus 1 is 2. Okay, the variance of B is scaled up by 100 on the winning side, 200 on the losing side, and you subtract off this 1 square dollar, but the numbers are massive now. Okay, so just to give you an idea of what the size of this thing is, 102 squared is roughly 10,000. You multiply that by 2, you get roughly 20,000. 201 squared is roughly, 200 squared, that's roughly 40,000. Okay, so you have roughly 20,000 plus roughly 40,000, that gives you roughly 60,000 divided by 3. That's roughly 20,000. Okay, so that's what you should expect this number to be. It ends up being 20,402. And just to put this in perspective, and I know this has been a while, somebody asked me when I first introduced the concept of variance, and we just had that one distribution where it was 50-50 to be plus or minus 1, or 50-50 to be plus or minus 1,000. It's basically a coin flip to win $1 or win $1,000. Your expected value is the same, but your variance is way, way higher. What does it all mean? Relative to what? Well, this game here has a positive expectation. You rate to win $1, but this is much more volatile. Game B is putting much more money at risk. Much larger, has much higher, we'll say higher risk. Okay, and we're talking about volatility. And probably most of you are in a financial position where you care a lot about $1. Sorry, don't care a lot about $1. It doesn't matter to you if you lose $1 with probability of third. If somebody takes $1, you're on a losing streak and you lose $10. It probably doesn't matter to you too much. But if you went on a losing streak here and lost 10 times in a row, you probably do care about $2,000. Maybe I'm wrong. Maybe I'm being presumptuous, but you probably do. Okay, and that's a lot of money to put in the way just to gain $10 on average, right? Okay, so here's how you analyze the situation, and a lot of gambling or stock market plays tie into this concept of volatility. All right. But you need another concept, and it's called standard deviation. Okay, most of you have done a standard deviation computation as part of grade school and high school. Okay, and what does standard deviation? What's the point of having standard deviation? Variance is in square units. So talking about the breadth of the main mean of the curve in square units might not be that useful. So you can take the square root, and when you do that, you end up in the original units. Now here we have a normal distribution curve. This is sometimes called a Gaussian, and I'm not too sure if I'm going to talk much about continuous probability at the end of the course or not yet. You might see this, but you've heard of normal curves, right? You've heard of bell curves. Bell curves have some nice optimized properties that densifies the data according to some metrics that have to do with variance and distance from the mean and all that stuff. And they were discovered by Gauss for some other reason. He was trying to do algebra. He wasn't trying to do statistics. Okay, but Gauss discovered it, so it's often called Gaussian curve. All right, so this curve, anyway, it has some nice properties. Not just that it's symmetric, but it's also densified in this nice way. And you can say how much of the probability density, and in a normal case, it's continuous. We take the integral rather than summing. Okay, so you take the integral under this curve, and there ends up being 68% plus or minus 1 standard deviation. Okay, so you ask yourself this question according to this 68, 95, 99 rule. How much of the curve is within 1 standard deviation of the mean? Well, it's 68% of it is. Okay, so that's sort of likely. How much within 2 standard deviations? 95. And 99 would be within 3 standard deviations. You can see this tail, it drops off really quick. Okay, binomials, the tail drops off really quick as well. There is 1% of the area in the entire tail from 3 standard deviations plus or minus to infinity. Okay, so when you've heard people talk about 3 sigma events, here's 3 sigma events. So this would mean that it is less than 1% likely to be 3 standard deviations away from the mean. Okay, so you would have to be super exceptional, or this case would have to be super exceptional for it to be believed. And maybe you are super exceptional. Maybe you're the best athlete, or the best student, or the best StarCraft player, or whatever it is. You're 3 standard. You're that good. You're that much better than everyone else, or maybe you're that much worse, and you should quit. Okay, same idea. Okay, 2 standard deviations or 3 standard deviations in the mean. These would be considered common events. And the tail, and we're going to be focusing a lot about the tail going into the next unit, would be considered rare events. And our goal in the next unit, just looking ahead, is we're going to try to bound the probability of an event being unlikely. Okay, so we're going to say that within 99% likely, you've seen these studies on TV, they talk about statistics, polling or whatever. They say with 99% likelihood it's going to be within plus or minus, whatever of what we said. Okay, one more thing before I go back to the second part of the example. Just want to mention what happens if you try to do something to the standard deviation. Okay, like what happens if you slide and stretch the curve? Okay, so if you have, sigma, maybe this is like sigma r, and you want to do, multiply it by a and add b, which is something that we did to, other quantities, and you're going to do that on your coming assignment. Well, it's going to change the variance, according to whatever its laws follow. And the variance of AR plus b, okay, so you slide it by b, the b goes away. This is going to be a squared variance of r. Which is equal to what? Not a sigma r, but, yeah. No, he said that. Okay, so a times sigma. It's not quite. You're very close. You're missing one thing. Absolute value. Okay, so if you multiply by a, it's going to multiply the standard deviation in a very natural way. It's going to stretch out everything by a. Okay, keep this in mind. Okay, let's go back to here. Okay, so the expectation of each game is +1, so you should definitely play this game if somebody offers you, and you should play it as much as you possibly can. But let's say you play 100 games. Okay, what sort of money do you expect to have after n independent games? Okay, so the game, the game's not rigged or anything, but if you were the casino, you would definitely have the edge over the player. Here, you're the one that has the edge. You should definitely play as much as you can. It's not that the expectation is going to change, right? Okay, so after n independent games, the expectation of, I guess, NA is equal to n times the expectation of A, which is $n, and same thing for B, right? So you're definitely going to be plus n, right? Here it's $100. Okay, but the variance of the n games is going to be the sum of each of the variances, right? And they're all independent. So the variances add, and in the variance of A game, right, it's 2 plus 2 plus 2 plus 2 n times, so it's going to be 2n. The variance of B played n times, or A plus A plus, so I should probably write that as A plus A plus plus A. Okay, this is B plus B plus B. Okay. Anyway, this is going to be 2,402n. And the reason this matters is because, if we're looking at the most likely thing to occur, it's going to be within some number of standard deviations of the mean. Okay, so let's just assume it's 1, all right? 1 standard deviation from the mean. Okay, so assume the range to be within 1 standard deviation of the mean. Okay, so game A is going to have a win of n plus or minus the square root of 2n. Game B is going to have n plus or minus the square root of 2042n. Okay, and if you take the coefficients of each of these, okay, so it's n, so it's 100, right? So we'll do it for 100 in a second. So this is plus or minus 1.41 root n. This is n plus or minus 143 root n. And when n is equal to 100, your net gain is 100, but you're much more steady in game A. It's going to be plus or minus $14. Okay, so you're going to gain $100. You might be down, to 86, or you might be, really lucky. You're up to 114, that kind of thing. You're going to be pretty close. Here it's going to be 100 plus or minus 1430. Okay, so your expectation is still positive, but you might be down 1400, and that would be reasonable. Okay, I mean, you should keep playing, but this is low risk to get your $100, and this is high risk. Okay, so this is why, if you've ever gone to a financial planner, or I don't know, you will eventually, they're going to ask you a bunch of intake questions about, how they put a bunch of returns on investments of various things. They ask you, what's your risk tolerance? Okay, so there could be investments where, you put in $100 and there's a huge upside if you get lucky. The company is going to do really well. Maybe there's a 10% chance that's going to happen. It's going to, multiply its investment by 20 times, but it has a 90% chance of going to 0, which might not sit very well with you, or close to 0. Okay, so you say, okay, well, that's like a huge upside. Like, on average, I'm doubling my money, and you're absolutely right. And if you make enough of those bets, it will converge over time. But it's much higher risk. People who are not going to live very long, or much longer, like me, you might want to. I might want things that are a little bit more low risk. Yeah, Yeah, so I'm just talking about one standard deviation, so this is, you're absolutely right, this is within 68%. Two standard deviations would be a little more certain, 95%, but then this amplifies by 2, right? So plus or minus 2,800-ish. Yeah, so there's still a 32% chance you're going to be outside of these margins, yeah, so it'll be either less than 86 or higher than 114, yeah, exactly right. Thanks for that. Okay, other questions about this before we move on? How did the variance come about? You played A independent games, so you can imagine that, sorry, I should have been way more explicit about this. It's like A1 for game 1, A2 for game 2, AN for game N. And because they're all independent, their variances just stack, linearly. They just add linearly. And then same thing for game B. So you just multiply by N, and then when you take the square root of that, it scales according to the square root of N. Yeah. But that's where that came from. Good. I'm teaching you about gambling. I feel good about that. And you're going to have some fun games on your 5th assignment, which is going to come out this afternoon. And you're going to make some decisions about what's best for you. And I'd like you to write stuff about what's best for you. It's actually, the questions are written that way. All right, so give it some thought about what you think risk means to you. Okay. Next, Teresa, we'll wait. We are, primed to talk about how expectation and variance can be wielded to draw conclusions. And this is the last mandatory unit of the course. Just as a brief review, there are 2 metrics that we have taken that describe or help to describe the distribution. One is the expectation. Where is the distribution centered, okay, as a weighted average of things? And there are 2 formulas. One used the PDF, the other one used the probability function. And then there's variance. Okay, so variance tells you how far apart things are. There are a few different things that we talked about. There's the variance itself, which is the weighted average of the square distances from the mean. Covariance ties 2 things together. How much are they entangled? And of course the standard deviation. Anyway, they all talk about the spread. Okay, so how spread things are. First thing, if you only know about the expectation, what can you draw as a conclusion about the tail? Okay, the probability of the tail. As an example, we're going to use IQ. A lot of you have heard of, what's your IQ and all that stuff. IQ is something that was developed by psychologists as a way of measuring how smart people are. They came up with a bunch of questions and did a bunch of math to take your score divided by your mental age to come up with this number that was normalized to be centered at 100, and eventually, over time, it had a standard deviation of 15. Standard deviation is not part of this problem, but it will be in the iterations of this problem that are to come. So more on that. Anyway, in this problem, just want to mention the expected value of the IQ is 100. That's one thing that we know. It's also a non-negative number, okay, which is important. If we were to draw this thing out on a graph, all of the distribution can't be over here. Okay, this is in the forbidden zone. Okay, but we know that the average is here. Okay, so that's the expected value of IQ. And we're asked the question, what's the probability of having an IQ of 300 or more? Okay, so let's see, that would be 200. Let's say that's 300. Okay, so we're asked to sort of estimate or bound the probability of stuff that's over here. Okay, so let's just talk a little bit about intuition. Okay, and the intuition of average to me means that, this is sort of like a seesaw, like it's like the middle, how a seesaw works, right? Okay, there's things on one side, pan balance, right? There's things on one side, there's a fulcrum in the middle. Okay, so whatever is above the average, okay, has to be balanced by something that's below the average. And if, we're looking at things that are 300 or above, that can only be balanced by things that can get as low as 0. Okay, so there's some lower bound to how much you can put on the other side to counterweight this 300. And furthermore, this is 200 away from, it's plus 200 away from the mean here. 0 is only minus 100 away from the mean. So for every one person that has an IQ of 300 or more, there have to be 2 that have an IQ of 0. And these are pretty extreme IQs, right? This distribution would have to be pretty extreme for that to happen. Okay, but that seems to be a limiting factor, right? Any probability that you find for somebody that's 300 can only be counterbalanced by someone that's over here. And that would be the most extreme situation. So probably, you can only have 1/3 of it over here. And that would be if 2/3 of the rest of the population actually sat at 0. Okay? We know that's not true, okay, because most people are pretty close to 100. But that would be the most extreme thing that we could write about mathematically, okay, just by knowing what we know in this question. Okay? So intuitively, it can't be too high, because any IQ above the average must be balanced by an IQ below. Okay, the best case, or the most extreme case that will allow us to have the maximum at 300, is that 2/3 of the probability has an IQ of exactly 0 to balance 1/3 of the probability having IQ 300. Okay, the second part of this problem asks for 150. And again, you can say similar things, right? I mean, the best you can do, the most you can fit there, is probably 2/3 of the population being 150, because you only need 1/3 of the population to sit at 0 to make that happen. Okay, so similarly, at most 2/3 can have IQ 150 or more, because if it was higher, we get a contradiction, and it's just by using the expectation formula. So the expectation of IQ is the sum over everything in the range of the weighted average of this thing. And if we just pay attention to the group that's bigger than 150 or bigger than or equal to 150, this is at least 2/3, greater than 2/3 times, sorry, I got this backwards, so it's 150 is the weight times 2/3. Okay, so it would end up being greater than 100. Okay, so this is the first thing that we learn is Markov's inequality, which just makes conclusions based on the average, how far you are away from the average. Okay, so it goes as follows. If R is a non-negative random variable, has to be non-negative, has to be an end, otherwise this counterbalancing argument doesn't work, then you can make a claim for this. You can say the random variable, the probability the random variable exceeds x is less than or equal to the expected value divided by x. Okay, so we had 100 over 300, that was 1/3. 100 over 150, that was 2/3. Okay, so it's bounded above by that. Proof. There are a couple of proofs, and depending on which book you read, you might see a different proof. I like this one. And it's to use the law of total expectation. Okay, so here we go. The first case that we do is R is greater than or equal to x. Okay, so we say the expected value of R given that R is greater than or equal to x. Okay, and of course we scale that by the probability that R is greater than or equal to x. And the other case is R is less than x. Okay, so this is based on the law of total expectation. Okay, so we're going to look at each of these quantities. We're going to approximate them, right, in the exact same extreme way that we did for the IQ, right? So we looked at the case where it was 300. We sort of assumed that it was 300, and that was sort of the edge, the knife's edge case. Okay, so the expectation of every case of R, where R is at least x, is the expectation is at least x. Okay, in the best case, it's x, where everything is equal. And in the case where R is less than x, we sort of make the assumption that it's 0. That was the conclusion we had, but really all we need is that this is at least 0. Okay, so this is greater than or equal to x times the probability R is greater than or equal to x, plus 0 times the probability R is less than x. And I wrote that down a little bit facetiously, of course, we're multiplying by 0. Okay, so I just wanted to show you the approximation that is going on here. We are throwing away something that is positive, non-negative, I guess. Anyway, we have the expected value of R is greater than or equal to x times the probability that R is greater than or equal to x. So we just turn that around. So that's a proof. And a nice corollary off of here is that you can talk about how far R is away from the mean in terms of multiples of the mean. Okay, so if you're 3 multiples away from the average, then you can bound the probability by 1 over the multiple. Okay, now there's a little caveat about Markov's inequality, and that is it's not saying anything particularly strong or exciting. Sometimes it's exact, sometimes it nails the distribution exactly, it's actually equal. But if you think about it, like we're saying, the probability that, that people have an IQ of 300 or more is bounded above by a third. I mean, duh. Like, I don't know anybody who has an IQ of 300. I don't know anybody, okay? Same thing for 150. Like, there aren't a lot of people in my universe that have an IQ of 150. I know a lot of smart people. I work with them, right? You know a lot of smart people. You go to school with them. Not many of you have an IQ of 150, sorry. But we're bounding above by 2/3. It's not very astounding. Okay, but sometimes it nails it right on. Okay? We'll save the examples for Monday, though. Okay, so and then we'll bring in the variance into this into the mix. Today's the last day. I brought the midterms with me, so if you haven't picked up your midterm yet, please get it today. After this, it'll be available in my office. Thank you.